So we're talking about pseudoaxial and pseudoequatorial and envelope conformations, and I was saying that in general, there's not a big difference between pseudoaxials and pseudoequatorials, except and axial and equatorial, except at this flagpole position, this envelope position up here, where the equatorial is better because it's actually almost straight away. It's not like equatorial in a normal chair. It's not straight away from the rest of the chair. It's kind of at an angle. Like it's
Mhm.
more or less equatorial. It's more or less horizontal, but it's not quite. Whereas in a flagpole one, it is almost exactly horizontal. So it's actually really good. It's pointing away from everything. Whereas the pseudoaxial substituent on this guy is the absolute worst thing you could possibly have because it's banging over everything else. The other pseudoaxial ones are okay, and the pseudoequatorial ones are, okay. But
Okay.
it's really this flagpole one that's really the big problem.
And like how does like the up down up stuff work with
Same,
the cyclopentane?
same. So
Okay.
pseudoaxials they interconvert. So the
Okay.
axial-equatorial, like if I take a look at this, the up position here. Sorry, I'm trying to find my mouse. The up position here is
Hmm.
pseudoaxial. The up position here is pseudoequatorial. The up position here is pseudoaxial. The up position here, I guess here actually it stays pseudoaxial because you kind of have a plane of symmetry.
Okay.
Axial, then it's equatorial, then it's axial.
So the back carbons like across from the flagpole would.
Yeah. Well, think of it as like it's a six-membered ring, but you deleted one of the carbons,
Okay.
but you're not changing anything else really. But because now they're not, it's not a chair, you don't have that symmetry thing. You now have this flagpole substituent that you didn't have in a normal chair.
Hmm. Okay. Okay, that makes sense. Thank you.
Mm-hmm. Any other question? Okay, Rose.
Hello. I just wanted to make sure that for radical chemistry stuff, for termination, we have to draw like all the different options, right? Except for polymerization, not like just basically one.
Yeah, I think that's it. Yes. Yeah, it's not. I guess it's not. I think that's it. Yes, that's it.
Okay,
So
so
for normal radical reactions, when you're not doing polymerization, there are always three terminations because you're always going to have radical one, radical two, and you can do one and one, two and two, or one and two.
okay, but not for polymerization because
Yeah, polymerization is tons of options, and I don't really want to mess you guys up, so I'll accept any termination at all, as long as it's a termination.
okay.
Yeah,
And then for LCAOs, if it's of a molecule that has resonance, do we draw it for the most stable resonance?
doesn't
Um,
matter.
it doesn't matter.
Nope, as long as it's for a reasonable resonance structure. Like if you draw for an unreasonable resonance structure, I'd be a little bit surprised. But the what's really going to be important isn't so much where the double bonds are; it's where are the p orbitals. So where are the potential pi bonds? And that's the same no matter which resonance structure you draw.
Okay. But
Because
like you're only drawing the pi bonds from one of the resonance structures.
right, and you just pick one.
Okay. Okay. And then just to confirm, I was a little confused when you said this like way back in the course. Um, for the LCAOs, do we have to draw the lobes and all that when you asked for that in a question?
The You don't need to draw the SP3 mini lobes, like
Like the other
the
side of the
nubbin lobe on the
yeah.
SP3. Yeah, you don't need to draw it. It just confuses the image.
But for LCAO, we're drawing like all the lobes, right? That's like what it is asking for, right?
Yes.
Okay.
But you're excused from drawing those little mini lobes on the other side of the SP3 for that.
Right.
Because they just mess up the thing. But everything else you need to draw.
Okay, that makes sense. Um, Okay, and then I remember you saying that electronegativity, or like in a column, no, sorry, in a row is more important than like the size in a column, right?
Um,
For comparing stability of negative charge.
yes, generally, I'm not going to. I'm not gonna make you try and pick between those. Like the one diagonal, like going diagonal by one spot, is where it gets a little bit tricky, and there's no real rule. Um,
Like if you had like nitrogen, oxygen, and sulfur,
yeah,
like oxygen is better than nitrogen as far as electronegativity, but then sulfur is better than oxygen as far as
right.
size.
Yeah, so sulfur is the wins all that. But I wouldn't
Okay,
ask you to do phosphorus, nitrogen, oxygen,
right.
because it's kind of the diagonal is going the wrong way. You don't have everything going. The oxygen still wins. The row is generally more important, but there are some exceptions in the halogens, and I don't want to get into that.
Okay,
I'm not going to ask you to do that.
okay. And then just to compare, when we're drawing chairs, like does it matter like where we put it in the chair? Like,
Nope,
okay, it matters like in relation to other molecules, but like where we start to do the ring.
not at all. Doesn't matter at all. There are.
Okay,
If I draw a molecule like this, and I say, provide me the chair of that molecule, making sure that the methyl group is on the top side of that chair, there are 6 right ways to do that. And if I don't
okay,
say that, there are 12 right ways to do that.
okay,
Yeah, actually, probably 24. There's a lot. You could draw a lot of different chairs, and it'd all be correct. Yeah.
okay. And then when it's like draw like the two chairs, right? Because like it can be like axial or equatorial. Um, do we have to like? Can we just like flip it from axial to equatorial on that same carbon, or like
Well, if
I'm
you
a little
if you
confused
flip
with
it from
like the
axial to
chair flip.
equatorial on that same carbon, you'll be
Pardon?
flipping it. If you flip it from axial to equatorial on that same carbon, you'll be taking it up and making it down, which will be a problem. If I
Oh,
take this and I say flip that from axial to equatorial on the same carbon, I get that, which is not the same molecule because that's well, it is in this case, I guess, because there's no stereo center. But this is up, this is down. That is not the same.
right. So you have to. That's what the chair flip thing is,
Yeah, if you chair flip it, this is not a chair flip.
right?
But
Um,
but if you depending what you like, if what you meant is
like if on the left side it's like yeah, like that.
and you moved it there, that's fine. Yeah,
I see. I see.
absolutely.
Okay, that makes sense.
That's fine. I
Okay.
erase that and put a big check mark.
Okay. And for naming, I'm just a little confused. Do you want the numbers for the like double or triple bonds before the like root name, or like in between like the root name and the like ene or ein?
You need to write the you can put the numbers for the double or triple bonds like where it is, either before you start the final name or sort of known to een ein or whatever.
Right.
But if it's E or Z, you need to put that up front with the R and S's. You need to write sort of 2E, whole name of compound, and then indicate the 2 for the een again. I'm not sure it
Okay.
made sense there.
I'm not sure.
So if I have this molecule, I can call this but to ene. I can call it 2-butene. But either way, up front, I need to write 2E butene because it's an E, not a Z double bond.
Okay. I see.
So I can put the 2 here. I think this is your question: is where do I want that 2? I don't give a shit. They're both correct.
Awesome. Okay.
But that 2E needs to be up front.
Okay.
Megan. I think you're up next.
Can we go over R and S conformations, please?
Sure. Do you have a specific example, or can I draw something? You can tell me if it's a reasonable example.
Yeah, I'm looking for something, a molecule that has like a compound in it, like F3C or something.
Okay. So just got a quick question. I was related to the last one from Emmanuel in the chat. Get on the right page. For determining what is heavier for EZ, you say we look at the A value. No, heavier for EZ, you look at molecular weight follows the same rules as RS. Yeah, its atomic number follows exactly the same rules as RS. The A value determines which one's more likely to happen, which one's more stable, but it doesn't tell you which one it is. Things want big things trans. And that comes down to A values. But for naming EZ, it's all about weight. Okay, something with this. So how about you tell me if this is a good example? I'm just going to randomly draw something.
That is a good example.
That is a good example. Okay. So I think the best way to approach these questions, and it doesn't matter, I could have drawn a humongously complicated molecule and said, tell me the stereocenter of this molecule, of this atom. That would be completely fair. And I think I'm sure I've done that. What we can do is let's just reduce this down. Let's objectify this atom and reduce it down to its basic constituents, which is that. And now all we need to do is assign priority to the different groups. And we're just going to say, hey, let's just give these numbers. So let's work through this one together, Megan. So I don't want you to be muted because I want to see where to help you with this. I want to know where you're running into trouble.
Okay.
Okay. So if you're looking at this, what would you? So we need to assign 1 to 4 priorities. Like there's no way around that. That is what we need to do first.
Yeah, I don't know how to do that. Like, is it like someone said in the chat? It's atomic number. Is that like?
Yeah, it's
is that all I have to
atomic
focus
number.
on?
It's atomic number. So the
Okay,
lightest atomic number gets the biggest number.
So all like CF3 would be number 1.
Why?
Because F3 has a higher atomic number than anything else in it.
Right. So what I'm going to do is I'm going to slightly modify what you said. And I'm going to say CF3 is going to be number 1 because fluorine has an higher atomic number than carbon. So what I'm doing is I'm not worrying about the F3 as a unit. What I'm doing is I'm looking at them as individual fluorines. So I'm going to this and I'm saying, okay, this is a carbon attached to this carbon. That's also a carbon. That's also a carbon. We are tied. We have a 3-way tie at this point. So to break that tie, I need to start following down one of the chains that this carbon's attached to. And by chain, it's a single atom. It's a fluorine. So the heaviest thing this carbon is attached to is a fluorine. The heaviest thing this carbon is attached to, not going backwards, is a hydrogen. The heaviest thing this carbon is attached to is a carbon. Fluorine is heavier than carbon. So that's number
Okay.
I never even get. These could have been 2 hydrogens. It doesn't matter. I never even saw them. I never even got to them. I never even considered them. They never came into the conversation. Because I broke the tie at the first fluorine. So this guy here will be number 2. For the same rationale, the carbon is heavier than hydrogen. This guy here will be number 3. And this guy here will be number 4 because hydrogen is lighter than carbon.
And the hydrogen wasn't attached to anything but the carbon.
Yeah, exactly. And it doesn't even matter. Like we don't even need to worry about that because we've assigned 1, 2, and 3. Everything else is heavier than it. It's the lightest. We could have actually assigned this 4 first because we know that hydrogen is lighter than carbon. Everything else is a carbon. This must be number 4. Once we have Once we have this, we need to put number 4 back and away from us.
Okay, but it's a 3D molecule. It can rotate both ways. Why doesn't the 4 rotate towards the 2 instead of to the 3?
You can. Nothing wrong with that, but you need 4 back and away from you to assign RNS.
And that's where I get confused though, because like if it rotates 4 going to the 3, doesn't it go like R and then 4 to the 2 is S or something? So like I get two
Well, that's
answers.
because you're trying to. So exactly. So maybe this is where we're having a problem because you're sort of thinking about. I'm getting confused over where. So when I have a 3D model, I don't have my model kit at home. When I have a 3D model kit, when I rotate, I'm not breaking any bonds, right? It's the same molecule. I'm just moving it around, right?
Yeah.
Like I'm not changing anything. So what we need to do is we need to agree, if we're going to assign RNS, we need to agree on a common viewpoint where we can say, hey, you go clockwise or counterclockwise when you have this perspective. Because as you just pointed out, you move 4 to one side, 4 to the other, you get a different answer. So what we all agree is that 4 needs to be pointing back and away from you to be able to assign RNS. And if you move 4 to where 2 is, 4 is not pointing back and away from you. The only place where 4 is pointing back and away from you is if 4 goes where 3 is.
Because of the wedge thing.
Yeah, because it's a back wedge. That means it's going away from us. So the rotation I want to do is just around this bond. So I want to rotate so that 4 rotates to where 3 was, which means 1 rotates to where 4 was, and 3 rotates to where 1 was. Oops. So I'm just kind of spinning around this bond. Does that make sense?
No.
Okay. Do you have a model kit?
No. And I've been like looking for one, but I haven't been able to find one yet. I had my uncle try to look for his because he did organic chemistry in high school and university. But
Yeah. It's probably a little late to get one shipped to you. I think this is really, really hard to do without having seen it physically. I don't know if you want to like get a marshmallow and stick some toothpicks into it and color the toothpicks with different colors. That might help because you can make tetrahedra with marshmallows and toothpicks.
I've done that. I just don't get like it's like it's just not making sense. Like how is like when the 3 and the 4 like turn and stuff like but I don't get like it's just like when it turns the 1 moves to the like they're not in the same order though like it
No,
doesn't
but
go
so what I'm
1
thinking
3
is
4 still like it's
okay. I'm going to turn on my camera and I am going to look around my room to see if I have anything that I can use for this. Like you're asking a good question. This is a tough question to answer. Got pens. I have lots
yeah
of
like I've been using my pens and like my little beauty blender makeup things because they're different colors and
no, it sounds like you're trying hard. So like I get you. I'm really happy to help with this. Um, I'm not good with my hands, but I'll do my best. So kind of what we have is like this. This is a tetrahedron.
okay
So in the view that you have, so I'm going to just do the kind of view that you've got. I'm going to try and line up. My Microsoft Surface stylus is 2.
okay
This mechanical pencil is 4 because it's pointing straight down. This mechanical pencil here is 1. It's coming out towards you. This one you can't really see is trying to look at. You know what? I need to expand the camera so I can actually see. Yeah, that works too. But I just Oh God. There is no good way to do this with this camera. I'm really sorry.
No, I can see. It's okay.
Right, and this mechanical pencil here is 1. So it's coming straight out towards you. And what we're doing is we're rotating around this bond.
Yeah, okay.
So when I do that, the mechanical pencil was coming out towards you is now going back and away. The one that was down is now coming towards you. And the one that was going back and away is now going down.
Okay.
Like the order's changed, but I
Mhm.
haven't moved anything. My hand hasn't switched pens. I'm just rotating like this. And my wrist doesn't go that way. Yeah. I think it's. I don't know what else to say. The other thing you can do if you find, and I think, and Megan, I think you're right. That does work. Other Megan, I think, pointed out that the other thing you can do if you find this rotation really, really hard, once you've assigned this, you can just sort of, that says an H, and there's no right arrow for this. I'm going to just swap 3 and 4. And I'm not going to rotate anything. I'm just going to physically rip 3 and 4 and switch places. By doing that, I have flipped the stereo center. If it was R, it is now S. If it was S, it is now R. And so what I can do at this point here is I can assign, now 4 is pointing back and away from me, which is what I need. If you have trouble with rotating, this works, and it works every time. 1, 2, 3, that is counterclockwise, that's S. So after the switch, it's S, so before the switch, it must have been R. There, I'm not rotating, I am just switching groups. And if you switch any 2 groups on a tetrahedron, you make the enantiomer. So if you're having real trouble rotating, this can help.
Okay.
Yeah.
What's an enantiomer? I've been getting that with the one that starts with a D confused a lot too.
So an enantiomer is when all of the chiral centers on a molecule have flipped. So let's say you have 7 chiral centers, and they were all R. Now they're all S. That is the enantiomer. It is the mirror. It is a non-superimposable mirror image. So all the S's are R's, all the R's are S's. A diastereomer is when some of the chiral centers, but not all, have flipped. So if you had 7 chiral centers and they were all R, and now another molecule has exactly the same connectivity, everything's attached to the same thing, but you have your 7 chiral centers and 6 are R and 1 is S, that is a diastereomer. It's not a mirror image anymore, but it's all the connectivity is the same. So an enantiomer, all the chiral centers flip. A diastereomer, not all the chiral centers flip, but at least one does.
Okay. Okay, thank you.
Yeah. Okay. Drop my camera. Yeah, a diastereomer, I always say 2 or more because if it's well, no, you need 2 or more. You need 2 or more chiral centers in a molecule to have a diastereomer. If you only have 1 chiral center, you cannot have diastereomers because you either flipped 1 chiral center, you flipped no chiral centers. If you flipped 1, you have the enantiomer. If you flip none, you have the same compound. You can't have a diastereomer with only 1 chiral center. But yeah. So that's to answer your question. Deepan put into the chat. Okay, Fatima.
Hi. Can you hear me?
Yep.
I want to share my screen for a second.
Okay. I'll stop sharing mine. So Emmanuel asked, when do you have meso compounds? So a meso compound is, what it means is a meso compound has a stereocenter. Actually, it has to have an even number of stereocenters. It needs to have 2 or 4 or 6 or 8. And it has an internal plane of symmetry. So it is its own mirror image. So it's a compound that is its own, like, it has a superimposable mirror image. And if it's superimposable, it's the same compound. And that happens when you have two chiral centers. They are in the same kind of place in the molecule. One is R, one is S. So when you flip the R to the S and the S to R, you can superimpose them back on the original ones. So there's an internal mirror plane within meso compounds. Okay, yeah. Go ahead, Fatima.
Can I hear it?
Sorry, yeah, I can see your question.
Okay, so let's start with this one here. So for SN2 reaction, you said there is only one transition state, right?
Yes, there's only one transition state in SN2.
SN2 only, but there's not any intermediates.
No, there's no intermediate.
Okay,
There
but
is an intermediate, like you can get intermediates when you have something like when you have like you need to remove a proton or something, but the SN2 core thing itself has no intermediate. Right.
Okay.
So this one we have an intermediate.
Why do we have two transition states? You said-
Because the first step is an acid base reaction, the second step is an SN2.
Oh, I see.
So we start with something that's protonated. We need to remove that hydrogen first.
Mm-hmm.
That gives us an intermediate. That intermediate then does an SN2 reaction, which has no intermediate. You just have that transition state too. There's no intermediate there.
So the intermediate is from the acid-base reaction.
Right. So what we're doing is we're kind of like the SN2, all these things are kind of SN2, SN1, E1, E2. They're kind of like your fundamental building blocks, like reactivity building blocks, but you can string them together to make more complex things. They're kind of like letters, but you can string letters together to make words. So you can string different mechanisms together, one after the other, to make a reaction. And that's what's happening here. Is you have an acid-base reaction followed by an SN2.
Okay, I see. And I have another question. So for here, you said that I minus is more stable than F minus. How do you know which one is more stable?
How do I know?
Yeah.
So remember, as you go across the periodic table across the row, they better stabilize negative charges. So F minus more stabilizes negative charge better than O minus does. But as you go down a column, you stabilize charges better. So S minus is better than O minus, and I minus is better than F minus.
And when I stabilize the charge better, that means it came from a strong acid.
Yes. Yeah, HI is a stronger acid than HF.
Okay, I see.
And it's a stronger acid because I minus stabilizes a charge better than F minus. Like HI is a stronger acid than HF because I minus is more stable than F minus.
Okay. And I would like you to go over this question. See.
I think we just saw that at the beginning of today. I think Sforti just asked that question. So what particular part of it is confusing?
Why is it exothermic?
Because the product is more, because we're I minus is more stable than S minus.
Okay. And for this one here.
Yeah.
I would like you to draw it. I wasn't here at the beginning.
Oh, okay. So the only thing, maybe I can talk about it orally instead of drawing. I can save a bit of time there.
Okay.
So it's an exothermic reaction, which tells us that the transition state will look more like the starting material than the product by the Hammond postulate, because it's closer in energy to the starting material.
Yeah.
So we draw something that looks a lot like the starting material. We know it's an E2 elimination, which means that the hydrogen that we're removing needs to be anti-periplanar to the iodine that's leaving.
This hydrogen here?
Nope, the one we're removing. The alpha hydrogen, right. And that needs to be across from the iodine.
Oh, okay.
Otherwise, you can't do the E2 because you can't donate the electrons into the antibonding orbital of the Ci bond.
Okay.
And so we expect that the that carbon hydrogen bond, that carbon iodine bond, are still mostly intact in a transition state, because again, the transition state looks like the starting material.
Mm-hmm.
So we're starting to make the sulfur hydrogen bond. We're starting to break that carbon hydrogen bond. I should have drawn a dotted line between the two carbons to start to form the carbon-carbon double bond. And we're starting to break the carbon iodine single bond.
We started to break first this bond.
We're starting to form that.
Form.
Yeah, we're starting to break. Your mouse is maybe the visual and the oral is not lining up. You're starting to make the sulfur hydrogen bond.
Okay, and then I'm gonna break the sulfur carbon bond.
Nope, that's still fine because it's S minus. It wants to make another bond. It's got a lone pair it wants to use. You're starting to break the carbon hydrogen bond in the main molecule.
Okay.
That's why it's dotted.
And then why don't have the S here?
Because it's doing an elimination. So the S grabbed the hydrogen, and it's break. So the sulfur is grabbing that hydrogen. Here, do not move your screen. I'm going to annotate your screen.
Mm-hmm.
So the sulfur is grabbing this hydrogen, and what you're doing is we're breaking this bond. We're breaking this carbon hydrogen bond here.
Okay.
And what that does then is that and this is where I did make a mistake drawing this. I should have drawn this as dotted along here, because we're starting to make the new carbon-carbon double bond. And then we're going to break the carbon iodine single bond.
So when the sulfur breaks the bond between the carbon hydrogen, my ethyl group is going to come instead of the hydrogen.
Your ethyl group stays on the sulfur. Nothing happens to it. You're not doing anything with that ethyl group. It's just attached to the sulfur. It could have been any base. There's nothing. It happens to be S minus CH2 CH3. It could have been H minus. It could have been LDA. It could have been terpetolithium. It could have been hydroxide. That's just a base.
Okay.
So the base is doing an acid-base reaction with that hydrogen, which is the elimination.
Mm-hmm.
Yeah.
I think I get it.
Okay, you know what? What I would do is Mobius has a video on E2, E1, SN1, and SN2 reactions. Like I think they're included in sort of the learning things when you're going through the modules. You might want to play that or maybe look it up on YouTube. Just watching the bond formation, bond breaking, and those reactions.
Okay.
Yeah.
I'll check that.
Okay. Just turn down my sound because I have it really loud right now. Okay. I'm seeing some just questions in the chat before I move on. Is SN2 mostly exothermic? Yeah, I would say SN2 is almost always exothermic because it almost always goes in the exothermic direction. Like an SN2 is fully reversible. You can imagine the SN2 going the opposite way with because what was a leaving group could become a nucleophile, kick out what was a nucleophile into a leaving group. And you're always going to go the way that is exothermic. So I want to be a little cautious about saying it's always exothermic, but almost always. Do meso compounds change the 2 to the greater n when you're... yeah, Mariam, yes, they do. They can subtract it by 1. Because you'll sort of get two fillings in that equation. You'll get 2 entries in the equation, but they're the same compound. And if Fatima is done, or do you have another question, Fatima?
No, I don't have any question, but I'm trying to figure out how to stop sharing.
Oh, okay. I am going to. I'll stop you. Okay, I think Aying is next.
Hi, I'm just listening.
Okay. So Nadia?
Okay, could I share my screen?
Yeah, absolutely. So Miriam, how do we calculate that? You need to figure out. So while Nadia is sharing her screen, so Miriam's asking about how can we calculate the 2 to the greater than n formula for stereoisomers when you have a meso compound. Just subtract by 1. Identify that you have a meso compound. Subtract by 1, because you're only gonna have one meso option in there.
Can you see my screen?
Mm-hmm.
Okay. For this question with radicals with the alkenes,
Mm-hmm.
so I understand all of this up to here. And then once you get here, you have this radical and then it can do resonance to produce this one here. But going on to the next step, do you consider the most substituted double bond or the most stable radical?
I'm going to make a correction in my notes because this is wrong. You should get the most stable double bond.
Okay.
And I've been
One.
intending to do this for a bit. What question is this?
Assignment 4, I believe. I think it's 1C.
Okay, I need to correct that. Yeah, this has come a couple times, and I don't know why I've never noticed it before, but you're absolutely right. You should get the more stable double bond.
Is that always the case with alkenes,
Yeah.
or is it?
No, it's always the case with alkenes. They'll always make the more stable double bond, because I don't know what the hell I was thinking. That radical's in resonance, so it's not like it's not like those are two radicals switching back and forth between each other. The radical is in resonance. It's the same radical. It's kind of split between those two centers, and you're going to make the product that goes to the more stable transition state, and that's going to be the one that has the more stable double bond present.
Okay. And then for alkanes, like this example is the stability of the radical.
Yeah, you make the more stable radical.
Okay.
Yeah.
And then my other question was for the lab quizzes. I was just looking at them. I was kind of confused on how to assign EZ for like a cyclo.
Hmm.
I'm not sure if we have to know
Same
how
way.
to do that, but
So on your bottom carbon of the double bond is easy, right? Because there's a hydrogen and a carbon.
yeah. So it's up.
So carbon's heavier. Yeah, absolutely.
Okay.
So your up top carbon's a little bit trickier, but it's got two carbons attached. But one of those carbons, the heaviest thing it's attached to is a hydrogen. The other carbon, the heaviest thing it's attached to is a carbon.
Right.
So your two heavy groups are on the same side of the molecule.
So it's Z.
Yeah, it's Z.
So shouldn't this be RRSS?
Well, it being Z or E does not tell you if it's R or S for the resulting product.
Okay.
You need to assign. There is no setting for that, because one thing to remember that generally often works that you can do that. The thing you need to remember is boron is lighter than carbon. So if I'm looking at the bottom carbon there,
On this one?
oh, that's not correct, Felicia, Mariam. Okay, so that oh, sorry, Dr. Icor and I have disagreements about shortcuts, and I think this is one where you get into trouble. I'm going to annotate your screen. Do you mind?
Yep, go ahead.
So hopefully this works. I'm going to use my stylus and maybe it'll work. So if I look at this carbon here, and this carbon here, just look at this one first. I'm just going to call it carbon 1, carbon A, and carbon B. So carbon A, the hydrogen is number 4. The boron is number 3, because boron is lighter than carbon. This is number 1. This is number 2. And I know this is number 1 because this carbon here is this carbon. This carbon is attached to 2 carbons. This carbon is only attached to 1, so this one will win on the tie. Is that okay?
Yeah.
Okay. So carbon B, following the same logic. Hydrogen is number 4. The carbon attached to nothing is going to be number 3. And then I have a carbon attached to a carbon and a carbon attached to a carbon. That's a tie. Carbon attached to boron, attached to hydrogen. The boron is heavier. So I have that. Okay, so this one here is clearly R. This one here, well, we're not in the right orientation, so I'm going to do a rotation. That's also it's also R in this case. Okay, well, they're just wrong.
Would the
I
original
screw
be
up.
S?
I just
because
need
you
to check.
switched two of them?
Sorry?
Would the original be S because you switched?
I didn't switch anything, I just rotated.
Oh, okay. Okay, never mind.
That's R. I'm making sure I didn't screw up. I didn't screw up. No, that this is SS. This is R. Yeah, this is RR and SS. Racemic. I think if boron had been bromine, then that would have been heavier, and it would have been RSSR.
Okay, so the shortcut they gave us, like the Z and the E, should we look at that, or do you not
No,
disagree with the
it's not
shortcut?
really reliable because it really depends on the relative weight of things, and if it's a cis or trans addition across double bond. There's a lot of things that can. There's a lot of things where that can go wrong. Like a lot of things where that can go wrong.
Okay.
I like there are shortcuts that are valid shortcuts and that work like 95% of the time. I'd say that one probably works about 65% of the time, which isn't very good.
Okay, so we just have to do like the RS for
I think
each.
you do, yeah. I think I'd be very wary about not doing that.
Okay.
Like I'm really in favor of shortcuts. I love shortcuts. This is one I don't feel comfortable recommending.
Okay, thank you.
Any other questions, Adia, or that was the one?
Nope, that's all.
Okay, that's straightforward.
Okay.
Okay, Deepan or Deppen? Sorry, I don't. I'm. How should I be pronouncing your name?
It's okay. I emailed you a question last night. I'm not sure if you got it.
I'm sure I did. I'm sure I just probably said come to office hours.
Yeah, so I was just wondering if you could do that question.
Okay, I'll find it. There we go. Yeah, got it. Okay, I'm going to share my screen. And I assume there'll be some heat here. So basically, this is asking what the hell happens in this case. So, pre-initiation. First of all, we know it's going to be a polymerization. And we know it's going to be a polymerization because there's nothing there except the starting material and the radical initiator. That's all we've got. I'm not going to draw the mechanism for this. It's been video recorded multiple times. So
yeah, I just get confused with the initiation step, really.
Right. So now this is where we run into a bit of challenges because we just saw an example with allylic radical formation, which is definitely viable.
How do you know to attack the H and not the double bond?
Well, I'm actually going to show you that you're going to end up attacking double bond.
Okay.
I'm okay in the initiation either way. Again, you attack the weakest bond. This is going to be a radical stabilized, resonance stabilized radical, so it's going to be favorable. And as we just saw in a previous example, the more stable resonance form for that is to have, well, the more reactive form. I guess this is the more stable resonance form, but the more reactive one is to have the double bond more substituted. So we've made that now in a propagation. So this can do one of two things. This can abstract, and you can actually get kind of a bit of a mess with these things, and the polymers of these kind of allylic substitute ones can be a bit messy. I'd accept quite a bit of different things in your propagation for the mess, and I'm going to walk through a few different ways of doing this. So one thing this can do is just abstract a hydrogen from another molecule of the same. And if we do that, well, all we've done is we've migrated a double bond internally. We haven't really done very much. Another thing we can do is we can react that with my dog is losing his mind in the background, which tells me that the Purelator people are here with a Christmas present for my wife. It's a special type of bark he reserves for delivery people, because he's very brave until they, as soon as they turn around and walk away from the doors, when he starts barking. So I'm actually just going to quickly label my atoms. Because it's really easy to lose track. I'm not going to give an example like this on the exam because it can just go too wrong.
Okay, in initiation, is it okay if we tack the double one instead of the H or no?
Yeah, it is. For polymer, it is. Because what we're going to make is that, and now that's going to react with another double bond, and we can then propagate the whole thing.
Okay, and then do we just put the brackets around any two carbons that are repeating?
Yeah, but you need to make sure that you're putting your unit. So your unit for this is, like, this is going to react with something else, and our unit would be that, which includes this side chain. Like this side chain would be in the middle of the bracket because it's part of the monomer unit.
And then we just put N in the corner, like no numbers, just N.
Exactly. N tells you that there's X number of repeats.
All right, perfect. Thanks.
Okay, that was not my happiest explanation. I am actually going to do another one of these in class because I got a bunch of questions to do something similar again in class. So I'm going to make sure I do one more today.
Okay, we have class at 1:30?
Yeah.
Oh, okay. All right.
Yeah, there's one more class. That surprised me at the end of last class. I thought I was done. I have to say I was a little bit depressed. Okay, like you people and all that, but I think we're all ready for the term to be over. Okay, Megan, do you have a quick question? I can probably run through one more before we're wrapping up.
Yeah, I can my screen.
Sorry?
Can I share my screen?
Yes.
It says I can't share my screen. Okay. I'm actually going to skip this one because we're gonna run through the class.
Sorry, Megan, you're really cutting in and out. I'm having real trouble hearing you.
Is that better? Can you hear me better now?
Yeah, it almost sounds like you're moving rapidly back and forwards away from your microphone. But that's...
Yeah, I just had fun with it, so.
Okay, well, if you want to find... I can't really hear you, but if you can find a question you want to do, I'll try and anticipate what you're asking.
I just had a quick question about this last step here. How much of that mechanism?
So you're asking to go over the mechanism of that reaction?
Yeah.
Okay. There, that was loud and clear. I can do the mechanism of that final step there. I'll do that. We'll call it a day. Yeah. So I'll just share my screen. So if we've done the boration, the hydroboration, and we have a boron and we have a hydrogen, and then the second step is Sodium hydroxide, hydrogen peroxide. So the first step is, when in doubt, protonate or deprotonate something. If you have a strong acid or a strong base, it's probably going to be involved. It's exactly what we see here. Now, there's a boron. There's an O minus. Boron likes being both negative and neutral, because when it's negative, it's got 8 electrons. When it's neutral, it's neutral. So we just did nucleophilic attack on boron, and nothing left. Like it's kind of like an SN2, but there's no leaving group. So it's just it's an addition reaction. And nothing needs to leave because boron has an empty orbital. Because it's only got 6 electrons. So it's got an empty orbital, so it can accept something in a way that carbon can't, because carbon's using all of its orbitals. So we have this. Not stable because boron's negative. What we're going to do basically is we're going to do an SN2 using the boron-carbon bond to attack this oxygen to kick out that oxygen as a leaving group. So our nucleophile is the boron-carbon bond.
Okay, that makes sense.
And when we do that, what we end up with is this oxygen here. We haven't done anything to the oxygen-boron bond, so let's do intact. Then what we have is this oxygen can now come in and attack that boron again. And what happens there now, our boron has gone negative again. And it can resolve its negative problem by losing an oxygen. We gain an oxygen, lose an oxygen. We're going to lose the one we want to lose because we get to decide that. Well, if we don't lose the other one, we just go back to where we were. So we get that. And then we just protonate this from, like, I don't know. There's water in solution. And we go to the product, which has the alcohol.
Okay.
But this is where all the action happens, is right here with these arrows. And what we're doing is we're using a carbon-boron bond as a nucleophile to do
Okay.
an SN2.
Perfect. Thank you.
Okay, cool. I'm going to leave it there at 10 o'clock. So tomorrow... I said I'd say that you have the syllabus to study, and that it's everything on the syllabus except the carbon. So Brianna asked, "Are you going to give us a list of topics to study or not?" It's everything we covered in the course except the carbonyl stuff. It's all on the syllabus. It gives the chapters that are covered. It gives the subjects that we covered. That is the list. Because the way this exam works, because it's open book, and even if it wasn't, I still suggest you do the same thing, but it's even more valuable now because you can have it with you, is come up with sort of a list of yourself of your reactions and things that we've covered. Grignard reactions Grignard reagents are on the exam, or can be on the exam. But we're not going to do any carbonyl chemistry. But they're strong nucleophiles. Okay. Thank you, everybody. So Sheeta, Brianna, Adriana, and Emmanuel's already left. But if you guys have some questions that didn't get addressed and you want to do that, you jump to the front of the line tomorrow. Okay.